Hi, everyone. This is me, part one of two parts of my talk titled The Kähler-Ricci Flow and Holomorphic Vector Fields. And I'd like to thank Hoju for organizing this wonderful virtual seminar. Okay, so today I'm going to go through the outline of the talk first. So since the central topic is the Kähler-Ricci flow and its behavior, I'm going to first start off by defining the Kähler-Ricci flow, which I'll denote by KRF. And from there, move into talking about maximal existence time of the flow and provide like a concrete example of a case where the flow shrinks CP1. And then we're going to move into these estimates along the flow for holomorphic vector fields. And so I'm going to note the key observation that we're going to use and quickly go through that proof, and then talk about the two settings where we'll apply this type of bound to obtain necessary estimates to show diameter bounds and Gromov-Hausdorff convergence. And so the two scenarios are the case where I'm contracting exceptional divisors, or rather the flow contracts exceptional divisors. And the second case is when it collapses the phono fibers of a holomorphic fiber bundle. So the setting here now is we're going to be working in the complex case since we are working with the Kähler-Ricci flow and Kähler manifolds. So first we'll define Xn to be a compact complex manifold of complex dimension n at least 2. Then we can define our Hermitian metric, or write our Hermitian metric in local coordinates as Gij bar in this way, where Gij bar is a positive definite Hermitian matrix for all points on X. And associated to G, we have this 1-1 form omega, which is defined as this, the sum of Gij bar dzi, which dzj bar. And I will, in parts of this talk, also refer to both omega and G as a Hermitian metric. So I might use this term interchangeably. And we say that a metric is Kähler if and only if this real 1-1 form omega is closed. And so in local coordinates, that's the equivalent of saying that the partial derivative in the I direction of Gij bar k is equal to the partial derivative in the J direction of Gi k bar for all I, J, and k. Okay, and so I haven't defined the flow yet, but the flow will evolve by its Ricci curvature. And so here I'm going to define the Ricci curvature. And so it's given by a real 1-1 form defined as negative dd bar log determinant of G, where G is the Hermitian metric / Kähler metric we'll be working with. And so using this definition, you can see that up to scaling, so if I were to scale the metric omega by a factor of lambda for some real number lambda, because you're hitting it with log, it's not going to affect the resultant Ricci curvature. So in fact, this Ricci curvature is invariant under scaling of the metric. And the first Chern class now I'm going to define as being the dd bar class of the Ricci curvature. And so we're going to denote it by C1 of X equaling the dd bar class of Ricci of omega, which I use the square brackets for. And it can also be straightforwardly shown that the first Chern class C1 of X, which equals the dd bar class of Ricci of omega, is independent of the choice of metric omega. So for any metric omega on X, that metric's Ricci forms dd bar class will give you the first Chern class of the manifold. So here we have some examples of Kähler manifolds with a signed first Chern class. So in the case where you have positive first Chern class, which we call the phono case, a concrete example of this would be complex projective space, CPN. In the Calabi-Yau case, which is when the first Chern class vanishes, we have complex tori. And in the case of negative first Chern class, we have Riemann surfaces of genus at least 2. And of course, the first Chern class doesn't have to be signed, but the cases where it is signed are just easier to work with. Okay, and so now we'll proceed to define the Kähler-Ricci flow. And so it's going to be, we're going to let omega be this evolving metric. So omega will be a function of little t, which is time, and starting from an initial Kähler metric, which I'll call omega naught. And so a solution to the Kähler-Ricci flow satisfies that ddt of omega equals to negative Ricci of omega, given the initial condition that omega at time t equals 0 is this initial metric omega naught. And so you can see that since Ricci omega is closed, the flow preserves the Kähler condition. So if I put a d here, you see that that's not going to change over time because d-ing the Ricci vanishes. And so as long as you're starting the flow from a Kähler metric, the Kähler-Ricci flow will preserve the Kähler condition. So the evolving metric will always remain Kähler. And taking cohomology classes, we see that So this is a PDE, but here, if you just take the DD bar class, this reduces to an ODE. So you can see that the evolution of the class omega t is just going to be equal to negative C1 of x, with the initial class being the initial class of omega naught. And so you can easily see that you can solve for omega t's class, and that it evolves linearly. So it's going to be equal to the initial condition class minus TC1 of x. Okay. And so so we call a class positive if there exists a Kähler metric within it. And so you know that you want along the flow that omega t stay Kähler. And so what would be an obvious necessary condition is for the existence of the flow is for this DD bar class of omega t to stay positive. So I'll get into that more on the next slide. So here we're going to talk about the maximal existence time of the Kähler-Ricci flow. So like I mentioned earlier, a necessary condition would appear to be that you want to at least retain that the DD bar class omega t stay positive along the flow, or rather that the flow can only exist as long as that class remains positive, which is equivalent to saying that there exists still a Kähler metric within that class. But in fact, it was shown by Tian Zhang in 2006 that this condition is indeed sufficient. And so they show that there always exists a unique maximal solution to the Kähler-Ricci flow starting at omega naught for little t between 0 and big T, where big T is a maximal existence time, and it's defined as the sup over all small t, such that that Kähler class of omega t, which equals omega naught minus, or the class omega naught minus TC1 of x, stays positive. Okay. So now we will give a concrete example of what the flow can do. So we're going to work with CP1 as just our elementary example. And so we know on CP1 that there exists this metric called the Fubini-Sudi metric, which is in fact a Kähler-Einstein metric, satisfying the following, that the Ricci of this Fubini-Sudi metric is equal to 2 times the metric itself. And so if we can construct an example where we start the Kähler-Ricci flow at this initial metric omega naught equaling twice the omega Fubini-Sudi metric. And then we can define the flow, or define the evolution to be omega of t equaling 1 minus t scaled against omega naught. And we'll show that this in fact is a solution to the Kähler-Ricci flow. So if you take the time derivative of this omega t that we've defined this way as simply scaling the omega naught, so shrinking it in time, we see that, taking its first time derivative, you see that this is just equal to negative omega naught. And then by the fact that omega naught was equal to 2 omega Fubini-Sudi by this Kähler-Einstein property, essentially we get this equality. So omega naught is going to be equal to negative Ricci of omega naught, where I've again used the scaling invariance of the Ricci form. And then from there, I can plug in the fact that omega naught is also equal to omega t divided by 1 minus t. And then again, using the invariance under scaling, this again just reduces to negative Ricci of omega t. So the far left-hand side is the time derivative of omega t. The far right-hand side is negative Ricci omega t. So you find that indeed this definition of omega t satisfies the Kähler-Ricci flow. And so we know that CP1 is diffeomorphic to S1. And so you can sort of imagine the flow as like shrinking, S1 until it reaches its singular time, which is or max existence time, which is at big T equals 1. And so we get the shrinking phenomenon. Okay, so that was the case of when the Kähler-Ricci flow shrinks a manifold, and that sort of happens under the unnormalized Kähler-Ricci flow by the fact that we were working on a Fano manifold, so one where C1 of x was positive. I'm going to briefly now talk about how we can normalize the previously stated Kähler-Ricci flow such that volume is preserved along the flow, and so that you can in fact get the flow to exist for infinitely long, as opposed to having exhausted itself by t equals 1. And so what we can do to normalize it is to consider this normalized flow omega tilde of t, which we'll define as just being a slightly scaled version of the original metric. So we're going to scale by e to the t of omega, and then the time input we're going to change to negative e to the negative t plus 1. And so this plus 1 is just to ensure that omega t at time t equals 0 is going to have the same initial condition as omega at 0, or at t equals 0. And so then taking its time derivative, we have that firstly, if you leave the e to the t and you differentiate omega in dt, assuming omega satisfies the unnormalized Kähler-Ricci flow, we get this Ricci term, where we also get this other term coming from the derivative of the inside part at t. And the second term here, we're just differentiating e to the t, so nothing changes, and then the rest stays the same. And so writing this out, we find that this is going to be equal to negative Ricci of omega tilde, where we're going to use the scale invariance. So of omega tilde, and adding back this thing, which is omega tilde. Taking cohomology classes, we have that ddt of omega tilde as a class is going to be equal to negative c1 of x plus the class of omega tilde. And so you can then move one to the right, this last term to the left-hand side, add this e to the negative t factor, and find that as a class, solving this like simple ODE, that as a class, omega t is going to be equal to omega naught plus e to the t minus 1 c1 of x. And so we know that for all t positive, e to the t is going to be greater than 1. And so in fact, this right-hand side will always be positive from the fact that C1 of CP1 is always positive. And so we in fact can now extend the flow such that big T is infinite. Okay. So now I'll move into talking about the existence problem for Kähler-Einstein metrics, and I guess one of the big motivators for the Kähler-Ricci flow. So a Kähler-Einstein metric, like I sort of mentioned in the previous case, is a metric omega such that its Ricci form is equal to a scalar multiple of the metric itself. And so because we know that there's the scale invariance on the left-hand side, we only have to consider the 3 distinct cases where mu is either -1, 0, or +1. And so in 1978, Yau and Aus showed that for manifolds with negative first Chern class, they proved that there always exists a Kähler-Einstein metric lying inside negative C1 of x. And then in 1978, again, Yau showed that now for the case of the Calabi-Yau manifold, so those that satisfy C1 of x vanishing, there in fact exists a Kähler metric omega satisfying that it's Ricci flat in any given Kähler class. So starting from given any Kähler metric, you can find a Ricci flat Kähler metric lying inside that Kähler class. And so the proofs that Yau and Aus used to prove these things involve solving a complex Mongeon pair equation using a continuity method. But then, yeah, in 1985, Sau came and reproved these results using the Kähler-Ricci flow, relying on the fact that the flow up to normalization converges to the Kähler-Einstein metric. And so, as maybe it wasn't super obvious, but when considering the normalized Kähler-Ricci flows, you see that their fixed points are in fact Kähler-Einstein metrics. Okay, so now I'm going to talk about briefly a simple concept, which is like the parabolic maximum principle, which will come up multiple times later in this talk and in part 2 of this talk. So we're going to fix t, some number, could be infinite, and then if we have some function that varies in both space and time, which is smooth on all of the manifold across the time slice 0 to big T. If it satisfies this differential inequality, so that this like heat type differential inequality, ddt minus the Laplacian of f is less than or equal to 0, then in fact you can then conclude that the supremum of this function f on this whole product on all of x across the time slice is going to be bounded by the sup of the function at time t equals 0. And so this type of maximum principle will be useful for our flow because we might want to obtain bounds along for the evolving metric along the flow. And if we can prove something to this effect, then we can obtain those bounds, because at t equals 0, it's just gonna be some fixed metric or function or whatever. And so that allows us to get uniform bounds. So again, the above tells us that a maximum must occur at t equals 0 if this function f satisfies this heat type differential inequality. And also the same statement here still holds if you replace x by a compact set U, as long as the maximum of f is achieved in the interior of U and not in the boundary. And so we'll see in one of the instances later that in the case of contracting exceptional divisors, we will have uniform estimates away from the exceptional divisors. And so then we can use this maximum principle to conclude that within that you can exclude the case where the max occurs on the boundary and just assume that it occurs on the interior. And so you can apply this maximum principle and then bound it by its value at t equals 0. Okay, so now I'm going to state some other interesting results relating to the Kähler-Ricci flow. So first, I'm going to define some notation. If you have 1-1 forms, alpha and beta, we can define the trace of alpha with respect to beta by trace sub beta of alpha, which equals beta super I j bar alpha I j bar. And so Song Tian in 2007 showed that showed this particular heat type differential inequality, where if you have F taking x to y, a holomorphic map, and omega, a solution to the Kähler-Ricci flow, with omega y being a fixed metric on y, manifold y, then we have that for all points in the product space, like for x cross 0t, where that trace happens to be positive, that in fact, the time derivative dt minus Laplacian of log trace omega, the pullback of omega y is going to be bounded by some constant Cn times the trace sub omega of this pullback again of omega y, where in this case Cn is going to be, has to be the upper bound of the bisectional curvature of omega y. And so corollary of this it looks like a parabolic version of Yau-Schwarz lemma. And so it's saying that if Cn is negative, then you know that this right-hand side is negative. And so at a maximum, you know that the time derivative and the time derivative will be negative Laplacian, the time derivative will be positive, negative Laplacian will also be positive. And so that immediately gives us an upper bound on this trace. And so once you have an upper bound on this trace, because the omega is the subpart, that is equivalent to saying that you get a lower bound on omega with respect to this pullback of omega y. Yeah, so these types of inequalities are going to be fundamentally like the tools we have to prove the bounds along the flow. Okay, so here's another evolution inequality. So this was shown by Sao, and this gives us control of the trace of the evolved metric with respect to the fixed metric. And so in 1985, Sao proved that if you have omega, a solution to the Kähler-Ricci flow, and omega tilde, a fixed metric on x, then if this heat type differential inequality holds, so if ddt minus Laplacian of log trace omega tilde of omega is bounded above by c trace omega of omega tilde. So notice that they are in swapped positions relative to each other. Yeah, so then this holds, and this type of inequality can be very useful. Like if you have either an upper or lower bound, this type of inequality will allow you to achieve the other direction. And so here C depends only on a lower bound of the bisectional curvature of omega tilde. Okay, and another result gives us a lower bound of the evolving metric along the flow. So in 2006, by both Tian Zhang and in the work of Zhang, they show that if you have x omega naught and y omega y, two different Kähler manifolds, and zeta, a surjective holomorphic map taking x to y, then for omega, a solution to the Kähler-Ricci flow on x, satisfying that its limiting metric or limiting metric class is equal to a class on simply the base manifold, so omega y, for t finite, then there exists a uniform little c such that omega is bounded below by zeta, the pullback of omega y. And so this statement looks like the previous Yau-Schwarz lemma statement, but here I no longer have to assume, I have to make a different set of assumptions. We're going to assume that it's finite time and that these class conditions hold, but I don't have to make the assumption that the bisectional curvature is strictly negative, which was the case on the previous slide. And so in particular, this this inequality holds when x is a fiber bundle over y. And so this will become more useful to us in part 2 of this talk, where I'll go into showing the actual bounds when the flow collapses Fano fibers. Okay, so now I'm going to move into talking about holomorphic vector fields, because that's the second essential thing we need for this result / talk. And so if we have z1 through zn complex coordinates on x at a point P, then the complex tangent space is defined to be TP of x super this math BBC, which is like the direct sum of the 1, 0 parts and the 0, 1 parts. And so it's spanned by the 1, 0 parts and the 0, 1 parts. And so we can define a holomorphic vector field V inside the 1, 0 part on X by V equals basically like a linear combination of these DDZIs with coefficients V super I. So these are just, these are just generally smooth functions, but we're going to specifically assume, because we're going to, for holomorphic vector field, these V super I's need to be a holomorphic function. And so that is equivalent to saying that if you take its derivative in the DDZK direction, bar ZK direction, then it's going to vanish for all K. So it's just saying that VI is a holomorphic function. And so this type of V, which is this linear combination here, is what we'll from here on refer to as a holomorphic vector field on X. Okay, and so now we will state the key observation, and that is this specific inequality. So this was an observation made by Song Wan Kobe in 2011, and they show that for any holomorphic vector field V on X and omega, a solution to the Kähler-Ricci flow, we have that this heat type differential inequality, like ddt minus Laplacian of log of V squared with respect to the evolving metric omega is going to be less than or equal to 0. And so, alluding back to the maximum principle, if we can, like when we're working with such V by the maximum principle, this will give us that because we have it the right-hand side is less than or equal to 0, this will tell us that this quantity, the norm squared of V with respect to the evolving metric, is always going to be bounded by either its space boundary or its value at time t equals 0. And so then the aim of the rest of this talk is to use this type of inequality, or to choose the very specific holomorphic vector fields so that we can bound the metric in all of the important directions to conclude uniform estimates. So now I'm just going to prove this inequality, which is a straightforward computational task. So on a Kähler manifold, you can always choose normal coordinates. So those are coordinates such that at a given point, Gij bar is going to be equal to the Kronecker delta function. And you can also simultaneously ensure that for that metric, that its partial derivatives are all going to vanish. So at a point P, we're going to choose normal coordinates so that the metric itself is diagonal, or is rather Kronecker delta, and that all of its first space derivatives will vanish. And so then writing out this norm squared of omega of V, we see that that's the same as just in local coordinates writing G sub ij bar, V super I, V super j bar. And so then if we want to show this inequality, we're going to start by computing the time derivative of this quantity. We'll deal with the log aspect in the next step. So just taking the ddt derivative, we see that Vi and Vj aren't going to be time dependent. So the only thing that's evolving in time is the metric itself, and it's evolving by the Kähler-Ricci flow. And so that means that ddt of Gij bar is going to be equal to negative the Ricci curvature, so Ri sub j bar of the same thing. Okay, so now that was the easy one. Now we do the Laplacian. It's a little bit more involved. So the Laplacian is with respect to the evolving metric. So here we have the evolving metric G super ij bar, di dj bar of this inside quantity, which is just the expansion of this in local coordinates. And then by the fact that we are using normal coordinates, we know that all single first derivative, or rather all first derivatives are going to vanish. So the only terms that survive this, these two guys hitting everything in here is the second order derivative on the G. And these guys are holomorphic. So so the GAB bar only does not vanish if either it has two derivatives or zero derivatives. And so this first term is the case where it has two derivatives, and the second term is where it has zero derivatives, but then the two partials might hit the VIs. And so now we use the fact that the V's are holomorphic, and so you only get the mismatched one. So like if you hit di on VB bar, that's going to vanish by holomorphicity, and you take DJ bar VA, it's going to vanish. So you only get the two instances where it lands, so that they both are either barred or unbarred. From there, you can just compute things. And so di dj bar of GAB bar is in fact just equal to the curvature tensor written out in this way, because we're working in the Kähler setting and in local coordinates that are normal. And then this last part can be rewritten as just nabla v squared. And then once you trace over the curvature this way, you in fact just get that this is the Ricci curvature against this plus this term. Okay, so now we're going to try to convert this Laplacian to the Laplacian of the log. And so very straightforwardly, you can see that if you want to take Laplacian of the log of function f, that's going to be equal to the Laplacian of f over f minus this anomalous f squared function over f squared. And so filling that in, we can in fact compute that ddt minus Laplacian of log v squared of omega is going to be equal to this right-hand side. And so our goal is to show that this right-hand side is less than or equal to 0, because that's ultimately the inequality we want to show. And to prove the key observation that we will need to move forward. Okay, so to deal with that last term, we're going to use the Cauchy-Schwarz inequality. And so if you expand this all out, you have like a nabla squared. And so I expand the nabla squared out. And so the inside things in the parentheses here are just to expand v squared omega. And then using the fact that you have normal coordinates, you know that the single derivative landing on G will vanish. And the single derivative landing on, VB bar is going to vanish in this case. And so you're only left with basically the one term. So when DI hits VA and when DJ bar hits VL bar. And that's using holomorphicity of V. So now I'm just going to rewrite this again with the summation signs to make the next step of Cauchy-Schwarzing more apparent. So now I'm just rewriting it. Oh, and I'm also just going to use the fact that the metric is diagonal. It's in fact Kronecker delta, but I'm just going to use the fact that it's diagonal to expand it this way. So I and J bar have to be equal, or sorry, I and J have to be equal, A and B have to be equal, and K and L have to be equal. And so that's what we have here. And then you can Cauchy-Schwarz and see that this whole thing is going to be less than or equal to this thing to the half. So I'm Cauchy-Schwarzing this part and then the last, and then this part apart. So this is like piece one, then piece two. So then you're left with this times this coming from here. And then this term is basically the same. So you get this times this again. And since these guys are the same, you just get that they're square roots, you get a single power of each of these terms. And that in fact gives you what you want, which is that now the nabla on the absolute value of this, or on the norm of this, is simply equal to the norm of the nabla of v squared times v squared. And given that, you'll see, going back, you'll see that that in fact will be equal to this. And so we get that the right-hand side is in fact going to be less than or equal to 0 as desired. Okay, so now we have proved the key observation. The rest of this talk, or more so, I'm going to motivate what we're going to do in the next talk, is to then apply the maximum principle using the fact that we have this type of inequality to bound the evolving metric in the very specific directions of holomorphic vector fields. So we're going to strategically choose certain holomorphic vector fields in the next talk and use this type of bound to show that we can bound the evolved metric in all the directions along the flow. And so in the two cases, again, that I mentioned that we'll consider are the case where the flow contracts exceptional divisors, so we can choose any locally, sorry, I think I meant local holomorphic vector fields we need, as long as we have bounds away from the exceptional divisor. So in the first case, we're going to use the observation and apply it to local holomorphic vector fields to obtain local bounds, because in this setting, we're already going to have uniform bounds away from the exceptional divisor. And in the second case, we are collapsing the fibers that are Fano on a holomorphic fiber bundle, where the fibers that we'll consider are going to be projective space blown up at a point. And so in this instance, we need to, in fact, choose holomorphic vector fields that are global, because in this particular setup, we do not actually have like bounds away from the blow up point. So it's made different, and we have to be more careful about the vector fields we choose, because we need them to be holomorphic. And in this case, we need them to be global. They have to extend to the whole manifold. Okay, and so the rest will be continued in part 2. So I'll see you there. Thanks.